All right, so this is section 4.7 of Math 146, video number 2. In the first video, we talked about the sine and cosine sum and difference formulas. In this one, we'll use a little bit the tangent one. I'm not going to do an entire thing about tangent just because, again, it's not that important in the grand scheme. Not to say it's not important, but there are other ways to do tangent as well. And we'll do a couple of like establishing an identity, or basically an identity proof, and then we'll actually do a solving an equation using this stuff. So the one thing that I'm going to talk about with tangent is let's say that we want to verify, so this is going to be an identity proof, that tangent of theta plus pi halves is the same thing as the negative cotangent of theta. Okay, believe it or not, that is an identity. Again, not one that we use a whole heck of a lot, but it is an identity. All right. So this is what we're going to do. We are going to basically say that tangent is the same as sine over cosine, which is what I was trying to say before. So we know that tangent of theta plus pi over 2 is the same thing as sine of theta plus pi over 2 over the cosine of theta plus pi over 2. And you might ask yourself, well, why can't I just actually use the tangent formula that you gave us? Well, if you try to do that, the problem is because you've got your angles as theta and pi over 2, there's no issues with theta. The issue is with tangent of pi over 2, because that's part of the tangent formula. Tangent of pi over 2 doesn't exist. It's an asymptote. So we're going to break this up into terms of sine and cosine. So once again, the idea was if we were to take sine, it's going to be sine of the first angle, cosine of the second angle, keep the positive sign here, and then it's cosine of the first angle, sine of the second angle. And we're going to divide that by, we'll do the cosine part. So cosine is both the cosine angles, so it's cosine theta, cosine pi halves. Flip the signs, so it's minus, and then it's the sine of the angles, sine of theta, sine of pi halves. So now we can simplify this, and let's see what we get. So first of all, cosine of pi halves is nice because that's 0. Since cosine of pi halves is 0, that's 0, and that's 0, which leaves us with cosine of theta times the sine of pi halves, but the sine of pi halves is 1, over the negative sine of theta, but once again, sine of pi halves is 1, so you get cosine of theta over negative sine of theta, which of course is the negative cotangent of theta. So that kind of proves that identity right there. That's the identity proof. And that's really the only one I'm going to do specifically with tangent. Otherwise, as long as tangent doesn't have an angle in it that's undefined, because remember, tangent has asymptotes at all the odd pi halves, you can use the tangent formula just like we did with the sine and cosine formulas and figure out the exact values. All right, let's do another identity proof. So our second example here, let's make that our first example up there. Our second example here was we want to prove this identity, that cosine of alpha minus beta over the sine of alpha times the sine of beta is equivalent to cotangent alpha, cotangent beta plus 1. And remember, the concept is you're supposed to try and work with the side that looks the more complicated. Definitely the left side, because of the fraction, makes it look more complicated. than what's on the right side, which is just a multiplication of a couple cotangents and adding 1 to it. So let's manipulate the one on the left-hand side. So the first thing I want to do is first I see I've got a cosine of alpha minus beta. Let's literally just write out what that is. So again, it's cosine of alpha, cosine of beta, and because it's a minus sign, we change it for cosines. And then it'll be sine of alpha, sine of beta. All that is over top of sine of alpha, sine of beta. So what we can do now is we can basically split this fraction. Okay, I can split that numerator up over the common denominator. So we should get cosine of alpha, cosine of beta over the common denominator, which is the whole denominator in this case. And then plus the numerator's second part, sine of alpha, sine of beta over sine of alpha, sine of beta. Well, that second fraction should make the most sense because literally that's the same thing over itself, so that's 1. And then over here, we have cosine of alpha over sine of alpha times cosine of beta over sine of beta. Well, since the angles are the same there, those are both cotangents, so we get cotangent of alpha, cotangent of beta. And that indeed is equal to what we had at the beginning. So that's kind of proving that identity. So just using the sum and difference formula to simplify that just a little bit. All right, let's go ahead and do one example of a solve where you might have to use some of this stuff. Okay, this last example is not going to seem very obvious. Hopefully it'll make sense after we go through it, but you might think to yourself as we're doing this, who in the heck would ever think to do this? Well, there are definitely mathematicians that, believe it or not, do think this stuff. I myself am probably not one of those who would have come up with this in a very short amount of time. That is for sure, not without seeing an example first. But it does make sense. So we're trying to solve the equation sine of theta plus cosine of theta equals 1. We're trying to find the values of theta that make this true. If it was sine squared of theta plus cosine squared of theta equals 1, then any value of theta would have worked, but it's not squared. So while you can actually use a squaring technique to solve this, and believe it or not, I think that's probably the easier method, I want to show how you would use a sum and difference formula. So again, this is not going to seem intuitive, but what we're going to do is we're going to actually divide both sides by the square root of 2. So we are going to divide both sides by the square root of 2. So in doing so, now I can split the left-hand side to be sine over the square root of 2 plus cosine over the square root of 2, or another way to write that would be 1 over the square root of 2 times sine of theta plus 1 over the square root of 2 times cosine of theta equals 1 over the square root of 2. So I probably could have just said, let's multiply both sides by 1 over the square root of 2. It works out the same way. But the reason that we did this is because this now looks like a sum or difference formula, because I have something times a sine of theta plus something times a cosine of theta. And if you think about it, because it's got a sine and a cosine and basically split up by that addition sign, this has to be a sine of an addition. So this has to be sine of two angles being added together. You can call the other angle whatever you want to. But whatever that alpha was is what gave us those 1 over square root of 2's. So if we kind of write this out, that would be sine of theta cosine of alpha plus cosine of theta sine of alpha. Well, I've already got the sine of theta and the cosine of theta in each one. So what that's telling me is that cosine of alpha, let's use orange, cosine of alpha has to be this 1 over square root of 2. And sine of alpha has to be this 1 over the square root of 2. Well, if you rationalize 1 over the square root of 2, that's root 2 over 2. And we should recognize that. We're going to need that. So from that, we're going to say, okay, cosine of alpha has to equal root 2 over 2, and sine of alpha has to equal root 2 over 2. So if that's the case, then there's really only going to be a couple of values that this works. Alpha here is going to be pi over 4. It would also be 5 pi over 4. I'm sorry, no, they're both positive. Yeah, both positive. That only happens at pi over 4. I don't know what I was thinking there. I was thinking where they were the same sign. They would both be negative in the third quadrant, so they would be the same value, but they would both be negative. So that really only happens at pi over 4. So ultimately what this says is that sine of theta plus pi fourths has to equal 1 over the square root of 2. Okay, so this is kind of like I said, this is not intuitive in any stretch of the imagination, but we're getting to the point where it should make sense. So now that we've got this, I can say, okay, so where is sine? Let's just write that as root 2 over 2. It's easier for most people to see. Where is sine going to equal root 2 over 2? Well, of course, that's going to be at pi fourths and at 3 pi fourths. That's within one circle. So that's what this angle right here is. But that angle is theta plus pi fourths. So how do I solve for theta? I subtract pi fourths on both sides. So theta here, subtracting pi fourths from itself is 0. Subtracting pi fourths from 3 pi fourths is 2 pi fourths, or pi halves. So those are the two solutions to this original equation, sine of theta plus cosine of theta equals 1. Again, not a very intuitive process, but it is a way that you could go about solving this. Again, the other way would be you literally could have squared both sides of that example right there using a little bit of foiling process, and you end up with the same results. The problem is you end up with a couple of extraneous results that you have to go back and check to make sure that they work, and they don't. So you eventually still get to 0 and pi halves. All right, that is all that we're going to do for this video. That finishes up 4.7. We have one more section to do in Unit 4, which is going to be some more formulas, which we're going to cover. It's going to be double angles, power reducing formulas, and half angle formulas, all of which are going to be useful specifically in the calculus portion in Calc 2. So we'll come back with that video, and that's about it.